we're going to build on basically the introduction to schematic design, where we have this like really simple circuit where we connect like power here. The power is going to run through the resistor, which is going to limit the current that's flowing through the LED. And yeah, this is sort of like the very most basic sort of circuit that you can do. So I'm just going to like quickly revise that for everyone. And we're going to go on to how do you first create a schematic like this? How do you take that and turn it into an actual PCB? So a board that you can have sent to a manufacturer, designed, and shipped to you. So that process is, it's called actually like designing the PCB, the physical PCB. This section here is the schematic, which is when you open KiCad and make a new project, it will create these two other files in the project structure. The SCH is standard among, KiCad and Altium. It just is your schematic, your schematic, where you define all of your electrical connections, all of the components that you're going to use, and all of the pins. Once we do that, so obviously this is like very messy right now, but we can just focus on this little block here. We've defined all of our connections. We've defined all of our nets. We can see where the current is going to flow. And I guess the last thing that we want to do is figure out what this resistance will be, but we'll do that in a minute. Once you do that, each of these symbols here, you can imagine that they're actually like a real like physical device. And you need to define that physical size, and what's called the footprint is basically where this device is going to connect to the copper on the PCB. And so every different component has a different footprint that we have to assign to it. And then once they're assigned, we're going to bring up the PCB in here. So it's just loading. Now this is the second half of PCB design. We're going to put all our components in here, define our board size, and then route traces between the different components. And so those traces are going to act like wires connecting the different pins to all of the different components that we're going to have on the board. So if everyone's up to this stage here, I'll quickly remind you how to construct something like this in KiCad. So after you download KiCad, you can bring up this, basically you create a new project, open the schematic file, and you can start placing components by clicking here. So obviously you want some sort of idea of what you're going to create beforehand. But today we'll just talk about having like a terminal block where you connect power. That's going to lead into a resistor and then an LED. So once you connect power to the circuit, the LED is going to turn on. When you remove power, the LED is going to turn off. So very, very simple. So if you click this part here and then click anywhere in your schematic, it'll bring up the symbol library. And I think last week we had an issue where for some people the libraries weren't loading. And so the first time you download KiCad, it will probably ask you to import the default libraries. You want to say yes to that because KiCad is open source, and so people are constantly adding new parts which are found on DigiKey or whatever like supplier that you typically would get parts from. They'll always be adding accurate components to this open source library. And the great thing about KiCad is that you don't really have to go search for them yourself. They're just all already here. So for example, for these like very simple passive parts is what we call them, like a resistor and an LED, we can just type in R, find the resistor that you want for the moment. So yeah, if you go online, at some point, you're going to want to actually define what parts you're going to buy, right? So there's like millions of resistors out there, and all of them might have a different like manufacturer, have a different footprint size, have different properties, which will suit your use. But for things like resistors, capacitors, I guess inductors, LEDs, these are very, very, very basic parts. And so normally we just put in a very, very, just like a standard symbol to represent that part before we actually go out and actually search for the exact part number that we want. So for example, here, DigiKey is a very popular supplier. There's a few others like Mouser and like Element 14. But to start off with, I just always get a DigiKey for all my parts. So say we want like a 10 kilo ohm resistor. We can search that, and for this like series, I'm going to try stick with surface mount components, typically because this is more, everybody uses surface mount components these days. Through hole parts are much easier to work with, but like they look a bit silly. Like, you're going to be making electronics that look like they come from the 60s and 70s if you use through hole parts. So if we click surface mount here, then we have all of these things here. These are all resistors, and they're probably all 10 kilo ohm resistors. Oops, chat. So this here is DigiKey. You're gonna search DigiKey. Yeah, and just click the first one, DigiKey Australia. And so this is a supplier for all different parts. And these are all resistors here. So typically, when I started out doing PCB design, I came onto DigiKey and I looked through all of these resistors and I tried to find one that, seemed popular. I didn't really have any rhyme or reason to pick any of these. But I thought you had to pick an exact component and then find out its exact footprint to then put it on a schematic. But what I've learned is really all you do is you just say, okay, I want to put a resistor here. We don't have to say what part it actually is, because resistors they all do the same thing. You can swap out this resistor for any other resistor. The only thing that is really like special about any given resistor is the footprint of it. So this footprint here, it's usually a number like 0402, 0603, 0805. That tells you how big it is. And so the size of it will actually determine the size of the footprint that you have to have on your board to solder that part to the board. And so it's all very standardized. I don't have to say, right, for this resistor, I want to use this 311, the yada, 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 or yada, yada, yada. You say, okay, I want a resistor, and then I can say, okay, I want this value. If you mouse over and press E, it should bring up the properties. And then say here, I just want 10 KR. Right, so that's going to be a 10 kilo ohm resistor. And then later on, when you do like your bill of materials, which is basically a list of the parts that you're going to put on your board, when you send that to your manufacturer, then you can say, okay, I actually want this part number to fill up that spot on the board. But you don't have to worry about that. Wait until the end. Cool. So for resistors, for capacitors, for LEDs, you have just like these very standard symbols. When you get into, not your passive components, but things like this thing here, this is what's called a low dropout regulator, or an LDO. And basically what it does is it takes 5 volts in to this pin, and it will drop that down to 3.3 volts on the out pin. These still come in like standard footprints, but you can't just put a generic LDO here and expect it to be able to like swap out between different components. This is where you want to actually like pick your part. So what this is the AP2112K. Will probably be on DigiKey. 12K. And so yeah, here we go. You want to pick your like exact part here about, okay, this is what I'm going to be working with. And the differences here, this one here is a 2.6 volt regulator, 2.5, 1.2, 1.8, 1.8, 3 volt. So we want like a 3.3 volt regulator. Actually, sorry, I'll talk about this later. But point is, for these like passive components, you can just put down a very, very standard schematic, and it, you can swap out to different part numbers. But for complicated parts, you can't do that. And all of these exist within, KiCad's library, which is, I guess, the main point of this. To do it there. There it is. Anyway, let's go back to this. So I think at the end of last week, we spoke about trying to figure out what size resistor we want to limit the current through this LED. And so the way that LEDs work is that once you hit a certain voltage, it's going to start conducting and let current flow through it. And it's going to kind of act like a short circuit. So basically, if we didn't have this resistor here, we just had 5 volts going straight into the LED, we're going to get 3.2 volt. So this is like the forward voltage of the LED. We're going to hit 3.2 volts across this, and then it's going to kind of be like a short. It's going to act like it's not even there. It's just going to be a wire. And then basically we're going to have 5 volts minus 3.2 volts, 1.8 volts across this wire. And it, when you short something, you're going to get a very high current, and that's where the problem, something's going to break. So what we need to limit that current is a resistor in series with the LED. So once we hit this 3.2 volts across the LED, there's going to be 1.8 volts left across this resistor. And since the LED acts as a short, after we hit the forward voltage on this, we're going to have 1.8 volts across that, and that, thanks to Ohm's law, is going to tell us how much current is going to be flowing through this circuit. So I think I left it last week saying, all right, what resistor value do we want to make it so that 15 milliamps flow through this circuit? And something I realized was that 15 milliamps might be a bit high for something like this. So I can't remember how many people still remember this. I don't know how many people still remember this, but JLCPCB is going to be the organization that we have our boards manufactured with at the end of this workshop series. And these guys have a service where they actually assemble, or they put the parts on for you, so you don't have to do it yourself, as long as you pick parts which are part of their library. So if you go to JLCPCB.com, go to resources and click on SMT parts library, you'll go to this search service, which is kind of like DigiKey. You can put in what you want into the search bar and it'll come up with all the different options. And from memory, I think last week we found an LED, which might have been like an 0805 size. So if we just search that and see what comes up. If it wants to cooperate. No. Okay, maybe I'll click down here. So on a light emitting diode, here are all our options. And I think we picked like an 0805 or a 0603, which are, different footprint sizes. And we will talk about that when we actually choose the footprints in a sec. Anyway, with all of these parts, it should normally say, how bright it is at a certain current. So here, okay. This is a very small LED, but it's suggesting, you're going to output this much at 5 milliamps. So let's go back into the schematic and we'll change our design requirements to be 5 milliamps. So we want to find out what resistor is going to give us 5 milliamps out here. And you can just like rearrange this. We want 1.8 volts divided by 5 milliamps, 0.005. Right, is that right? Okay, I think that's right. 1.8 volts, and we're getting 5 milliamps out. So yeah, it seems like we want a 360 ohm resistor, which to me seems pretty low, but maybe this being live, my brain is just not working. Yeah, okay, that's fine. Cool. So let's say that this is like 360. And that kind of summarizes what this basic circuit is going to do. So once we have defined all of our components, so we just have a resistor, LED, and a connector here, we want to go up to, want to do what's called annotating. We want to annotate our schematic. So at the moment, you can see that this is a resistor with a question mark. So every single part on your board is going to have some like designator associated with it. So you can be like, okay, I need to swap out R3. And you can go look at the schematic and be like, okay, this is what R3 is doing. This is where I can find it on the board. And this is like a problem part or whatever. So every part may as well have like a name. R is standard for resistor. So this is just going to be like, all right, resistor 1. The diodes are always like D something. Connectors are J something. And then like microchips, like microcontrollers, are like U something, if it's some like part. Inductors are L question mark. And there's probably, I think like transistors are Q question mark. But the point is, like, you don't want to be numbering all of these yourself. So you can annotate a schematic just like this. Annotation complete. And now you can see that here. So this is pretty messy because I have some other things I want to explain up around the place. Actually, let's delete these. When I hit annotate, we have, this is diode 2 on our board. This is resistor 3 on our board. And this is like connector 3 on our board. And so it needs, the schematic needs that so that the PCB side knows where to put, if you change this part in the schematic, it's going to connect that over to the PCB and change its footprint. Actually.
Excuse me, sorry. How did you get the annotate thing up?
So if you click up on tools, I think, yeah, tools and then annotate schematic, it should just be there. And don't worry about any of the settings. I just like click annotate. It should do it for you. Cool. Oh, cool. You can click there, annotate. So the next part, once you have your schematic annotated, you want to assign footprints to these. So this is where, your parts are going to actually become physical. And the way that we do that is we click up here next to the ladybug. We want to click assign PCB footprints to schematic symbols. And this is going to load up a library of all of our footprints. If this doesn't load, you might have to, download, kind of like I think we mentioned to Emma in Slack that you have to like download a GitHub repo full of all the different parts. And we did that for the schematic library, but you probably have to do that for the footprint library as well. And it normally it'll take a minute to load all of the footprints because these are a bit more complicated than just your basic symbols. So where's all my things going here? So maybe let's look at a resistor footprint is pretty simple. It'll just be like two little pads, and the pads will have like a width. They'll have a distance that they need to be apart from one another, and like a height as well associated with it. For the most part, you know, these sizes 04, 02, these are standard like footprint sizes for passive parts. You can get away with assigning like a 04, 02 footprint for a resistor, a capacitor, and an LED, and you should be pretty safe. If it's not, the hard thing is, at least in Altium, sometimes you'll find a part where you don't, you know, there's no footprint for it available. And so there's a whole process that goes into creating footprints for different parts, which isn't too bad, but it takes quite a while to get used to. And it's kind of scary because if you design the footprint wrong, then you're not going to be able to put that part on the board, or you're going to have to, have the board manufactured again. So you really want to make sure that, just use standard libraries for now. Okay, cool. So here, this is where we assign our footprints for the parts. So ignore these two. These are just like little, this is like a demonstration of a board that we might use later down the semester. And then this is an example of a dropout regulator. And this here is an example of a USB plug. But what we're worried about is these three parts here. So we got R3, D2, and J3. So I'm going to assign footprints. And we want to assign a footprint to D2. So a pretty good way to do that. Let's just like pick a very standard size footprint. So if you remember, we have 04, 02, 06, 03, and 08, 05. 08, 05? Yeah. Yeah, okay, I guess you got to click this to search for parts. Oops, what's happening? Oops. Ah, right, okay. Yeah. So here you have all of your different footprints categorized into different sections, and whenever you click on one, this thing here says you're going to be searching within that library, and then this here you're actually going to be searching for the part within that. So perhaps we can just use this for now, and we'll look for like an LED just to make it simple, or diode. LED, okay, here. So we got LED surface mount components. That's what SMD stands for. So yeah, we want to pick things that are surface mount, not through hole. Now here you have all of these like crazy options for footprints. I don't know what most of them are, but I can see here that we have like 0201 size, 0402, 0603, 0805, and this one here says that is hand solder. So this probably makes it easier to do yourself. So let's pick that, and then you just so make sure you have the diode assigned here, and then double click it, and that will assign the footprint to that component. Cool, okay, so now we have a footprint assigned for our LED. Here we have our resistor. So let's go to our resistor library, and we want a surface mount component, and let's pick a similar footprint. Yep, so 0805. That's like probably big enough. They're like still very tiny parts, but you know, you can probably handle soldering it by hand. But let's just do that now as like a proof of concept. Now, our footprint for our connector, what we're going to want, normally for connectors, you're pretty safe to pick like a through hole. So a connector is basically going to be these two little like pins that are sticking up, and we want to put that into the hole in the PCB and then solder the base to it. And by doing that, then we're going to have like this little terminal where we can plug things in. So our connector is like one row with two columns. So it's just two little pins that are sitting next to each other. And so we've got all of these like crazy options. Just gonna have a look and see what we want to pick. Oh, sorry, these are capacitors. Completely clicked the wrong thing there. Connector pin, yeah, this is what I want. So do I want pin sockets or pin headers? So sockets are kind of like the female plugs that you plug something into. And then, so it would be basically like this like little hole. I don't know if you've like played with Arduinos before, but it's kind of like the plugs on either side of that. And then the headers are just like the two little like pins that are sticking out and they're just like exposed. So we want to pick this one. 2.54 millimeters is the pitch. Basically means it's the distance between the pins, and 2.54 millimeters, I think, is like 100 mil. And when I say mil, this is something that you want to get used to in PCB design. A mil is 1,000th of an inch. And a lot of manufacturers, you know, use mil to talk about the size of things. It's like pretty standard. If you talk about like trace width or distance between traces, you know, you might want like a 10 mil trace width or like a 6 mil trace width. It's kind of annoying. It was, for me, it took a while to get used to using mil because it was a completely different measurement system, but a lot of the time it does make things easier to discuss, you know, if you want like like JLCPCB, they might say, oh, the smallest trace width that you can have is 6 mil. And that's better than saying like 0.1524 millimeters. Anyway, so 100 mil is pretty standard for headers in PCB design. And so we know that's 2.54 mil. So we want to pick, yep, this one, pin headers. And let's look down for a here. So this is 1x2 with pitch 2.4 millimeters and it's vertical, so it's going to be sticking out of the board. Cool. Now R2, let's just pick the same footprint as 360 as R3. So that was 0805 hand solder. Yep, okay, they're the same. And then, sorry, I still have this USB one. I'm just going to assign it. Just like a typical USB connector. But you guys probably don't have this in your schematic right now, so don't worry about this. Maybe I'll show you, because like USB plugs are a really easy way to provide power to something. You know, in the board I did for Sweep Aero, we charged the battery with a USB cable. And so basically all I've done here is I clicked over here to create a symbol. And I think I searched up like USB, yeah, just USB. And now there's a lot of different types. You probably know there's different types of, you know, USB cables. There's the standard USB A. There's Type B, which is, you know, like the really pretty like common one. And now there's like USB-C plugs, which are the sort of oval shaped ones. Pretty standard to use like USB type B, or like a micro USB. Probably micro USB. Oh yeah, it tells you the shape here. So that's like the shape that we're used to, I'd say. These are the USB-C plugs, and USB-A, just like the chunky ones that you plug into your computer. So maybe let's pick a micro USB type B micro USB, and we'll just place that into the schematic. I'm just going to delete this one for now. Yep. And now, so this is sort of like the first intro to using a symbol from a library. V bus just means like it's the voltage that sits on the bus, sits on the line. USB is 5-volt standard. So you're going to get 5 volts out of here. You can mouse over this pin here, press W, draw your wire out, press K to cancel it, right click, end tool. And then as we did last week, we want to put a net. So I'd say like this is like our 5-volt USB line. Press R to rotate things, by the way. So that's our 5 volts out. You know, USB has data lines, but we don't want to use our USB to actually communicate any data through our system yet. We just want to grab this like 5-volt. If you want to, we can either use our header or maybe we can use USB 5 volts. And then the other pins that are important are these ground pins. So ground, we'll want to, oops, sorry. You click over here to get your power port. Just type in GND to get our ground. And for USB, there's a lot of, basically these are differential lines which are very sensitive to noise. And so a lot of USB cables come with like a shielding system, which shield it from like RF noise and whatever else is trying to be introduced. And normally we just want to tie that shield to ground, so we can just chuck in a wire like that. Cool. Now, remember when you add anything, you want to annotate your schematic. So we'll just click here, annotate. Now this is labeled J1, everything's happy. And when we click back to our assigned footprints, we'll now want to put a, oh, oops. Lost everything. That's all right. Let's go down and add it again. So where's our LED? LED surface mount, 0805, hand solder, chuck that in. Then we want our USB connector. I saw that here. A lot of different types here. I have no real idea of what the best option is, but let's just like pick, Molex is a pretty popular USB plug creator, so we can just check that in for now. You can always change it whenever you want, so don't be too worried at this stage. Let's just like try to get something into our PCB. We want our 2.54 millimeter header, which was this vertical one, and then our resistors. So we'll go back to resistor surface mount, and we'll go 0805 hand solder. This one here. I'll put that on both of those. Cool. So we'll hit OK, and now we have all of our footprints assigned. Next step is to create this netlist. So this is going to create all of the connections that we need and all of our, basically, oops, all the information we need to create a PCB. So we'll just click netlist and just like leave it all as is, and we'll hit generate netlist. Going to ask you to save it somewhere. Default name's fine. And now we have just like a file which defines, it basically is a transferable format which defines all of the connections within our schematic. And we need that because we're now going to go onto our PCB. So if we go into the PCB project, you can open up the file which has .KiCad PCB, and you're going to get to this screen here. And what we want to do is import our netlist that we just created. So let's find, sorry if everyone got that. So we have load netlist here, this button, and then we want to find our netlist file, which is what we just generated. It should just be sitting here. And then we're going to click update PCB. Cool. So once we hit that button, it should import all of our parts. Oh, and you can just click anywhere. Cool. And so here they are. So these parts here is the physical size and shape of the part when it's on our board. So you can imagine we have like this little microchip, and these are all the pads where all the little pins are going to be coming out and soldered to the board. This is the special big thing here that we're going to try and use to build the flight computer later on. So don't worry about that now. It's just to show you what that looks like. Here, this J1, if you remember, is our, oh, it says it here, this is our micro USB plug. So you can see that it's just kind of like, it's a plug that sits here and then it has the pins out the back, which is nice. Here's our LED, our 100K resistor. I can't remember what this is for. Where was that? Oh, that's part of our regulator. Okay, I'm just going to leave that for now, because we'll talk about that soon. So these two parts, don't worry about it. Here's our connector. So I'm mousing over the part and I'm pressing M to move it. And then here is our current limiting resistor for our LED. Cool. So I'm just going to move it all closer to the middle. Now, the cool thing about a PCB design software is once you put parts down in your, this part, you can actually view it in 3D. So I think if you click view and then 3D viewer, all of these footprints should have a 3D model that's associated with them. And so once we do this, you can see here that there's going to be a 3D render of everything that we've done so far. So here we can see this is our STM32 microcontroller, this is our LED, little diode LED. This is the footprint where our USB Type B connector is going to sit. So it's going to have little prongs that stick through the holes here, and then we solder the pads we solder the pins onto the pads. This is our current limiting resistor. This is our connector to connect power, and then this is something we'll talk about later. So yeah, you can really quickly and easily see exactly what is happening as you assemble everything. So for now, let's move that away. We'll move these away. Oops. And let's look at our very, very basic circuit that we have going on here. Oops. So we have two options for powering our circuit. We have our USB plug, and we have our header. I think if you press Alt-3, yeah, okay, Alt-3 also brings up the 3D viewer. So this is our USB cable, and then you can put 5 volts here and ground here from like wherever you want to source that power, and that's also going to power our LED, which we're going to turn on. So something that you also can notice is that all of these parts have these tiny little lines connecting between them. So these are called rat lines, and they basically they tell you where you have to connect the pads together. So you can see that, here this is saying, all right, I want you to connect this part here to this part here. And this is how you really, you slowly go through and you connect everything up, and this guides you as you do that. So basically the first thing that I normally do is just rotate everything so that the rat lines are nice and happy, nothing's like crossing over each other, and you have like a clear idea of how you're going to connect things together. Something else actually we have to do is define the board outline. So let's do that now. So at the moment, our board outline, so this green part is the actual like PCB, which you can hold in your hands. This is being generated by KiCad is by default, just because we have parts that are sitting around here. What we actually want to do is define that outline ourselves. And so in KiCad, there's a layer here which defines your edges. And so if we click here, this edge cuts layer, we can then draw a shape. And this shape is going to be what defines our board. So make sure this little blue line is ticked next to edge cuts, and then we're going to find the line button. I think add graphic line. Let's try this. And then just click around, just like make a little square. So we'll zoom in, say, all right, we want our board to be like this big. Boom, boom, boom. Oops, made a mistake, but that's all right. Boom. And then right click and maybe just double click. There we go. So now we have this like outline for what we want. Obviously these parts are gross, so just like highlight them, delete. And this one here, you can just click the edge and drag it back. Now I'm wondering if this is going to be happy. Yes, okay. So now that we've defined our board outline, you can see the green part is only where we drew the edge cut. And this stuff is just sitting off in space now. So it's not generating the board outline for us. Cool. Yes, so now we have this little area to work within. As I'm sure you're probably aware, USB-C or USB plugs normally sit around the outside of the board, just so you can plug things into it. So let's start moving things around to where we actually want them on our final board. So you can try and put it like that. It might be hanging over a bit too much, but it's not too much of a worry. So these holes are going to exist here, and the pads are going to sit on top. So we can just see how close that is. And the plug is going to sit there. Oh, did not mean to do that. That's cool. Top view. Oh, nice. Now, yeah, let's work from the USB cable for now. So, actually, no, sorry, let's not do that. Let's work with this connector. Just because they're on different 5-volt lines. But that's good because then we can see how you update the PCB later. So this here, you're going to get, we want to put 5 volts here and ground here, and then run our power through this system and then back to ground. So how do you do that? Well, we have to actually route, we have to place tracks to be able to do that. And the tracks or the traces are the little wires that we use to connect everything in a PCB. So let's put everything like this. And we click this button here to route our tracks. But before we do that, we want to make sure that we're on this layer here. So all of these layers have some sort of special meaning. All we really need to know right now is that FCU is the front copper layer. So this is where we put our traces on the front. And then B is obviously on the back, is where you route your other traces, where you can put some more traces in a 2-layer board. And then I guess the other important one is silk screen for now. And this is where you like put graphic material. So say you want to like instruct the user that, this is 5 volts. You can put that on the silk screen layer, and then the manufacturer is going to print that on the board for you. So we'll select the front copper layer, and we'll click route tracks. And then up here we can see that our track is like 9.84 mil. That's fine. So don't change anything for now. Okay, and now we want to connect this 5 volts here to the 5 volts of the resistor. So once we click route tracks, you can just click in the middle here, and this is our wire that we're creating now. And so KiCad will tell you with this yellow line where it wants you to route it. So we can just draw a wire straight from here to here, click right in the middle, and there we go, we have 5 volts that connecting these two. Now we can click here because we've got a route line that's going to connect these 2 parts, and then we have ground going back to ground here. So if you don't like how KiCad is drawing your traces, like here, I don't really like this bend coming out like that. You can just sort of like click here to draw part of it, and then, like slowly construct your trace as you go. So now if we look in 3D, we have these wires now, which is connecting everything. So once we put 5 volts here, it's going to flow through the resistor, and then flow through the diode, the LED, sorry, it's going to light up, then go back to ground, and then go back to wherever we're sourcing that 5 volts from. Cool. Now, if we want to get all USB Type B connector involved in the fun, we can bring them over. And what you can immediately notice is that, yes, we want to connect our grounds together. So let's just go ahead and do that. We're on the front copper layer, click our routing tool, and our ground is going to go to here. And our ground also wants to go to all of these little pads here. So let's connect them all up. For whatever reason, these are ground. Cool. Now, yeah, you might think that, oh no, there's a mistake, because now the 5 volts that is coming in from the USB is different to the 5 volts that we're inputting here. And normally you will want them to be different. You don't really want to connect up different 5 volt sources without some sort of like protection between them, because everything could, they might be at very slightly different voltages, and so then there'll be a potential difference between them, and you'll get current flow and something's going to heat up. But for now, let's say we're not going to connect our USB plug in and our header plug at the same time. Let's just say we're never going to do, that. We want this 5 volts to come from the USB to also light up the LED. But there's no wire saying, okay, I want to connect this 5 volts to this 5 volts here. You see, it's not letting us. And that's because I've defined them as different nets. And so what we're actually going to have to do to tell them that they're, we want them to be the same, is to go back to our schematic. So we'll go back to our schematic here, and here's the problem. So we call this net here, this connection of wires, the 5 volt line, and then we call this our 5 volt USB line. So they're entirely separate, and KiCad is not going to let us connect them together. So say, for example, we do want them to connect together. We can delete that net, and then we just want to place this 5 volt symbol there again. Now KiCad is going to be like, okay, this bus here, this wire, this connection is going to be connected to this one, which is going to be connected to this one. So after we change something in here, you'll normally want to annotate everything again, check your footprints are still assigned all happily. Yep, everything's the same. And now you have to remember to generate this netlist. And then we go back into here and we generate the we load the netlist again. So normally you can just click it and then say update PCB. Now we can see that it happily allows us to connect the USB to the 5-volt line. And there you go. So obviously you don't want to do this because if somebody plugs in 5 volts from like Arduino and then plugs in a USB micro here at the same time, you know, they're going to be at different voltages and you're probably going to break something. But now this gives us the option to independently either plug in a USB or plug in, you know, 5-volt source here and light up this LED. And that basically summarizes the start of how you do this kind of PCB design. Once you have everything set up in here, then you can go on and create your like manufacturing files, which is just a couple of clicks in KiCad, and then you can send it to, you know, JLC, and they'll assemble everything for you if you use their assembly service. Obviously, this is like a proof. This is like a proof of concept sort of design. This is horrible. Don't do this. But now, hopefully, with these tools, you know, you can go out and create something yourself. But maybe not just yet. So I think we're coming towards the end of the session now. But next week, we're going to talk a bit more about what we're going to do for this flight computer. And we'll start doing a schematic for very basic parts that we're expecting to be on there. And then we can bring it over to our PCB and start hooking everything up. And so basically, hopefully at the end of the day, we're going to have something that looks like this. So we're going to want like a USB plugged in here. When you plug it in, a light is going to turn on to say that we have power. It's going to pass through this thing here, which drops 5 volts to 3.3 volts. It's a very important concept is, you know, transferring between different voltages in electronics. And then this chip here, which runs on 3.3 volts, we're going to figure out what, you know, things to connect to this. We're going to want to connect, for example, like a barometer to determine how high we are, an accelerometer to measure all the forces that is on the rocket as it's in flight, and probably like some form of memory so we can log all of that data to like a flash chip or something, transfer it to an SD card, so then we can connect it to our computer and then analyze, you know, what happened in flight. We can see all of the different forces. We can integrate that to try and recreate the flight path, figure out how high it's gone, and then build on it from there. Hopefully we can include like staging events, which is something I want to do. So for example, this chip will send a message to a circuit, which basically will like heat up some nichrome wire or something like that. And that is going to burn through some sort of, or maybe like ignite some sort of staging device. So like blow out a parachute or whatever it is. And we're going to talk about all the logic that needs to be on this chip to determine like apogee, when you want to like shoot out the parachute, when you want to you might want to like stage different parts of your rocket. I guess, yeah, that's all the plan for later on in the semester. But this is sort of the basics for now. Do your schematic, generate a netlist, bring it into here, route everything together, and, you know, Bob's your uncle. If you have any questions, queries, or concerns, please ask them. Whenever you're ready, you can, you know, shoot us a message in Slack. If you want some ideas on projects to work on in the meantime, you know, shoot me a message, send a message to the Slack, and we can all have a chat about it and see what you can practice on for the time being.